Good afternoon, dear friends. We continue to study processes in distributed element circuit. This is our second lecture. We will learn about the main feature of such circuits. In addition, we will introduce the concept of primary parameters that characterize these circuits. This lecture is the first step to a theory of circuit with distributed parameter. First, let's mention what we talked about in the previous lecture. So now is some conclusions of previous lecture. In the previous lecture, we found out that all elements of electrical circuits have some dimensions. Consequently, the parameters of these elements are not concentrated at some point in space, but are distributed in space. Therefore, circuits with concentrated parameter do not exist in reality, but are an idealization. So, we also found out that this idealization is possible only when the dimensions of circuit's element are much smaller than the wavelength of electromagnetic energy that acts in these elements. If the size of the elements are comparable with the wavelength, then we no longer have the opportunity to neglect the fact that the parameters are distributed in space. A typical example of an element with distributed parameters is an electric power transmission line. The old theory of electrical circuits doesn't work in this case, so development of a new theory is required. The basis of the new theory should be three laws which are subject to all electrical circuits without any exception. These are the first and second laws of Kirchhoff and as well as the communication law. If a distributed circuit is in steady state, then it obeys only to Kirchhoff's laws. However, before constructing a new theory, we need to find out what parameters characterize distributed elements. This will be the topic of our lecture. We now turn to study of the main features of currents and voltages in circuits with distributed elements. This feature determines the mathematical apparatus that we will have to use to calculate these currents and voltages. So, on the one hand, we know that when studying elements with distributed parameters, we cannot neglect their geometric dimensions. That is, we should take into account the extent of this element in space. On the other hand, we know that the propagation speed of currents and voltages is not infinite and has some value. From this, we can conclude that currents and voltages propagate along the element with distributed parameters. Currents and voltages will be different at each point in space that this element occupies. Therefore, both currents and voltages in circuits with distributed element are a function of the spatial coordinate. At the same time, we know that the currents and voltages may change over time. That is, they are functions of time too. Thus, current and voltages in circuits with distributed parameters are functions of several variables. The position of a point in space is described by three coordinates. Let's take into account the time coordinate, and in general case we can say that currents and voltages will be functions of four variables. Let's consider a simpler case. The image shows a line with distributed parameters. It has only one spatial coordinate. This is distance x, which is counted from the beginning of the line. Therefore, currents and voltages in lines with distributed parameters are functions of two variables, time t and spatial coordinate x. Let's try to present a graph of functions of two variables. If the graph is flat, then we can use only one independent variable. For example, distance, as you can see in this picture. We will assume that this graph shows the voltages, for example. The fact that the voltage depends not just on the x coordinate, but also on time, can be shown on a flat graph by driving several voltage curves. Each curve is the voltage depends on distance from some fixed point in time. This picture shows two voltage curves. The first is drawn for time t1 and the second is for time t2. Properly speaking, we should draw here a large number of other curves for other times. Therefore, a flat graph of functions of two variables is not convenient to use. A complete picture of the voltage change both in time and in space and can be obtained from the spatial graph. This graph is shown in this picture. The graph has two independent coordinates. Along the red axis here is the time, and along the green axis is the x spatial coordinate. This graph depicts a surface, each point of which corresponds to a voltage at a particular time t and at a particular point in space x. This spatial plot is much more visual. The fact that currents and voltages in lines with distributed parameters are functions of two variables greatly complicates the mathematical apparatus for the analysis. The mathematical apparatus becomes more complex because the operations of differentiating functions of two variables are more complex. Indeed, we can differentiate such a function both in the first and in the second variable. In this case, we obtain the so-called partial derivative of the functions with one of the variables. As we remember, in general case, Kirchhoff laws for instantaneous values of currents and voltages are differential equations. These equations include derivatives of coil currents or capacitor voltages. We found the voltage of the coil using the derivative of its current, and the capacitor current was proportional to the derivative of its voltage. In the previous topics of course, currents and voltages depended only on time, so we used the so-called Hall derivatives. In this case, differential equations in Hall derivatives were obtained, and we could find analytical solutions to such equations and obtain current and voltages as functions of time. The process of solving differential equations in total derivatives is not very complicated. In circuits with distributed elements, we must also find the voltages on the coils and the currents of the capacitors through the derivatives. Only now it will be partial derivatives on the time. But if we want to know how currents and voltages propagate in space, we will have to use partial derivatives on the distance. Therefore, differential equations for calculations current and voltages in circuits with distributed elements will be partial differential equations. The solution of such equation is much more complicated than the solution of equations in Hall derivatives. Moreover, modern mathematicals in many cases cannot obtain analytical solutions to such equations. Thus, the mathematical apparatus of the new theory should be the apparatus of differential equations in partial derivatives. These equations will relate the partial derivatives of current and voltages with respect to time and distance, but in addition to derivatives, these equations will also include some parameters that characterize distributed elements. Let's find out what these parameters will. As we know from previous topics, all elements of electric circuits have only three properties. These are conductance or resistance, inductance, and capacitance. Conductance characterizes the ability of an element to conduct an electric current under the influence of voltage. Inductance shows that an electric current in any element always causes a magnetic field to appear. Capacitance characterizes the ability of an element to accumulate an electric charge, that is, to create an electric field. Therefore, we can say that any element with distributed parameters has all these three properties. But the parameters of the element are distributed in space, so the question is, where exactly in space these properties are localized? Consider, for example, a line with distributed parameters, which has a length of L meters. We can say that this line as whole, relative to the output terminals, has equivalent resistance, equivalent inductance, and equivalent capacitance. These three equivalent parameters are due to the physical properties of the line conductors. It is clear that these parameters depend on the length of the line. It is known that the resistance of conductor is greater the longer its length. The same can be said about inductance and capacitance between conductors. But at the same time, we cannot ignore the fact that this is insulations between the conductors of the line. And this insulations is not ideal. We can model the effect of insulation by introducing another force parameters, conductivity between two wires. This conductivity also increases if the length of the conductors increases. Thus, the line as a whole is characterized by four parameters that can be represented by the equivalent scheme shown in this picture. But if we use this equivalent scheme, then we will have two problems. The first problem is that the equivalent circus parameters of a line depend on its length. The second one is that if we use this equivalent circuit, then we will only be able to calculate the current and voltage and the end of the line only at the end of the line, and will not be able to determine how these voltages or currents distributed along this line. The use of so-called specific parameters helps to solve these two problems. They characterize these parameters, not the line as a whole, but only one of its section of unit length. Let's consider a section of a line that has a unit length. In the international systems of unit, the length of the section is 1 meter. Let us assume that the parameters of the line are evenly distributed along this length. That is, any section of the same length has the same parameters. If we know the full equivalent parameters of the line as a whole, then the parameters of a single section can be determined by dividing the corresponding parameters by the length of our line. These line parameters are called primary parameters. They depend only on the properties of the line conductors and the distance between these conductors. Primary parameters are indicated by the index 0 and are measured as ohm per 1 meters, Siemens per 1 meters, Henry per 1 meters, and Farad per 1 meters. It is the primary parameters that we will use to calculate the currents and voltages in our line. Our lecture is over. Let's summarize it. In this lecture, we learned that currents and voltages in lines which distributed parameters are functions of two variables, time and distance from the beginning of the line. Therefore, the Kirchhoff equations for lines with distributed parameters will be partial differential equations. Solving such equation is a so difficult task then we can expect our topic to be mathematically much more complicated than our previous topics. Lines with distributed parameters are characterized by so-called primary parameters, which depend on the properties of the line conductors and the distance between these conductors. Using the Kirchhoff equation and the primary parameters, we will be able to create a basic equation for the line. This will be the topic of our next lecture.